Hi, I'm Al Boyer,
And I'm Anthony Zepeda.
and this is our final project presentation of the Synthesizer, our device.
So we're going to start off. What is a synthesizer? So just quickly, it is an analog synthesizer combining voltage-controlled circuits, mostly oscillators, to generate and shape sounds. We cut our synthesizer into four main parts. We have a main controller that's in charge of talking to the rest of the three parts. We have our general input-output, that's the user interface, where we have 12 keys through UART. We'll go over that a little bit later. We have an oscillator that's in charge of generating the four waveforms that we will output. And then we didn't get to it, but we have an ADSR filter that would be great for Rev 2, and we'll also go over that later in the slide. Just real quick, a little more in depth about our input controls. We have 12 notes, so we have a full octave. Just like a piano, we have 5 black keys and 7 white keys. They're controlled through UART and a GUI that we use on the computer screen. Once again, a great Rev 2 for us is we have potentiometers that we could use as knobs, just to control certain things such as the oscillator wave shape and the 4 parts of our ADSR that we'll tell you about a little bit.
Now let's talk a little bit about the inner workings of the synthesizer. A sound signal is, as you might know, a time-varying signal. And so in order to create a voltage out of a speaker, we have to create this time-varying voltage. Now, our digital device, an MSP430, has, as you know, on the out pins, a 1 or a 0. We don't quite have discrete voltage levels. So in order to get the, for example, discrete voltage levels of the sine, we resorted to using a PWM system in which a pulse modulated waveform is passed through a high-pass filter, low-pass filter, which cuts out the abrupt squares of our PWM input here and translates it into an overall DC offset. Now this alone is not enough to create a time-varying signal. In order to also get the variation over time, we have an additional timing circuit, which changes the PWM duty cycle over time in order to create different voltage levels. This, combined with the PWM filter, allows us to achieve different waveforms. This is enough for creating simple waveforms such as the triangle, sawtooth, sines, things that we saw in the digital to audio converter, sorry, digital to analog converter pattern. In order to get more interesting waveforms like the random guy over there or some of these weird sine guys going on here, what we have to do is start doing a little DSP, start mashing together waves. And what we do is that we have several different counters for each of our signals, and we add each of these signals together. For example, if I want to add a saw and a sine together, I just take voltage here, add them together, divide it by 2, and that creates a combined voltage here. That is then spit out to our output, which is just a simple LM Class D audio amplifier and into a speaker, creating our wonderful sound.
And as we'll see later in our demo as well, once we start mixing these waveforms together, we get some pretty neat and interesting ones.
Part of our Rev 2 plans is to implement the ADSR envelope. Now, part of music is, of course, the characteristics of a sound. We've seen sines and squares so far, but that's not all that an instrument has. For example, a trumpet and a piano might play the same note, but they sound very different. And part of that has to do with their ADSR envelope, which is a characteristic of our sound. There are 4 parts to it in general. You can imagine, for example, if a sine is playing here, let's say that this has an amplitude multiplier with 0 and 1. So an ADSR envelope would be, okay, when an instrument starts playing, it has a time to get up to its maximum volume. It has a time to get up to what we call a sustained value, which is where it'll stay while it's holding. And then it is a time to release to 0. We would implement this using an operational transconductance amplifier, which is basically a fancy voltage-controlled current source, which we could then use to add 2 voltages together to create this sort of compound signal that we then spit out to our speaker. Again, this is all Rev 2.
Yes, and like we mentioned earlier with the potentiometer knobs, we'd be able to vary each of these times, thus creating many more signals and many more outputs that we could hear. Real quick, the basic requirements of our system is you want to be able to take inputs from serial commands and a variety of analog and digital inputs, and be able to produce a full range of audio output signals. This was just so that we can make it easy for a beginner user to hook this up and then immediately begin producing music. And also we would like to allow for filtering of the audio output in order to create interesting sounds. This would be more of our Rev 2 with that ADSR filter, just to increase the complexity.
Lessons learned. We learned a few lessons from this project. Our first and biggest lesson, ironically, is to start small, then go big. We had big dreams for this project. Our original design involved digital potentiometers, I/O expanders, all kinds of op-amps all over the place, several MSPs talking to each other, no less than 5 SPI devices. The list goes on and on. Needless to say, this piled up over time, and with things not coming together as quickly as we anticipated, things did not quite turn out as we had hoped. The lesson, therefore, is to start out small, building things that work, and then adding on, instead of trying to create an overarching design and then hoping you can build inside and that everything stays together.
And that nicely goes into our second lesson learned, is having a complete scope of the project before beginning it really helps. We kind of understood what we wanted our final product to do, but we didn't think too much of in terms of what we needed on the inside to do that. So when it came time to implementing everything, we ran into a lot of interferences, and it made it very difficult.
Our third lesson is to use the right tool for the job. While the MSPs are very useful, they are 16-bit, mostly integer math devices. Meanwhile, in our project, we're doing a lot of digital signal processing. We could have been much better served with, for example, an MSP 432, which uses a Cortex core, which is a 32-bit core with a built-in floating point unit. That would have made a lot of our math a lot easier because it would have had built-in support for multiplication and additions and lookups. Would have made a lot of our tables a lot smaller and a lot of our math a lot easier. In addition, we could have cut down on most of our cores and a lot of our components because it just has more pins.
Yeah. And our last lesson learned is when you're designing a project, everybody thinks about the hardware and the connections, if you have enough pins, and that's great, but you can't forget about the communications. We found out we could connect everything, but when it came time to having everything talk to each other at the same time, we ran into a lot of conflicts. It's easy to get 2 devices to talk together, but as soon as you add that third one and you're trying to get 3-way communication, it becomes a lot more difficult.
As we mentioned, we have several Rev 2 steps for our synthesizer. As mentioned, we have an ADSR envelope. We also plan for bigger oscillators. This includes such things as polyphony, which is the support of several notes being played at once, more waveforms in our wave tables, more oscillators supported, and more effects such as filtering and LFOs.
Also for our Rev 2, we wanted to go with how it looks and make that a little bit better. We wanted to add an LCD display